This is an example of working the hard or level 3 problems on the Inverse Laplace Transforms game in Circuit Tutor. So as always, I do have examples available here at multiple levels of difficulty. And of course, I've already watched the introductory tutorial that explains the basic principles involved, which would be important before starting the exercises. But let's just look briefly at an example. And this will show you a fully worked problem of this type. And if you're having any difficulty, it would be a great idea to look at some of these examples before you attempt the exercises yourself. So in this case, I have a function that has an exponential function of s, which indicates a time-shifting property based on the properties of the Laplace transform, which are available here. And then, so I can basically split that up into the exponential times this function, which is called f of s. And using the time-shifting property, then also notice that I have to factor this quadratic in the denominator. So that's done using the quadratic formula. In this case, it has real roots, and so it would be expressed this way. And then partial fractions is performed on that, as indicated here, since we have two real roots, or poles, in other words, at -6 and -2 inverse seconds, respectively. Then the partial fractions expansion is done here, using the method of residues, or the thumb method, if you will, multiplying through to find each of these K0 and K1 terms, which are then substituted in. Then we take the inverse transform using the table, back to exponential functions. Those are combined, and then finally we do apply the time-shifting property because of that exponential function to get the final result, which is down here. Okay, so again, that will show all the steps if you need to review that, and it'll show problems of all the different types that are available on this level. And there's also user-selected examples here. For example, if I wanted to look specifically at a partial fractions problem involving complex conjugate poles, such as you might see on this level, I could do that, or any of the other types. And it could include time-shifting factors there to look at examples in a different way. Okay, so let's go into the hard level problems on Circuit Tutor. So in this problem, we do have an exponential function of s, so that does indicate we're going to need to use the time-shifting property. And again, if you forget what that is, you can always go to the Laplace transform properties table here. And the time-shifting property is this one that's shown here, which involves the exponential function of s multiplying some other function of s. Excuse me. So now, it's helping you kind of go through that by defining this as the exponential times another function called f of s, which is then everything that multiplies the exponential. And the first step here, we have to be sure to watch what it's asking us to do, is to just factor the quadratic term in the numerator and or denominator here. There's only one in the denominator in this case. So we're not being asked to do the partial fractions yet, and we're certainly not being asked to do the function of time. That's why it says f of s equals to this. So if we started putting in time domain terms, doesn't matter whether it's the right final answer or not, that's not what it's looking for at this stage. So we need to go into the Laplace domain instead, because it's looking for a function of s, which is the Laplace transform variable, or the complex frequency. And basically, it wants us to re-enter this with this term being factored. So we will need a fraction, of course, as the original has. We will need a constant in the numerator, and then the s plus a term in the numerator. We can fill that in if we like as s plus 11, and then the 10. And then we will need two s plus a factors in the denominator so that we can properly factor it. So we'll place that down here. And now in order to factor that, we can use the quadratic formula, the standard way to factor a quadratic expression. And I'm going to do that with the aid of a scientific calculator here. So let's bring up my TI-84 Plus emulator. And I will use the standard quadratic formula. Remember, this is a(s squared plus bs plus c. So the a is 1. This is generally always the case here, if you put it in standard form anyway. The b is 18, and the c is 72. So the form of the quadratic formula I like to use is negative b divided by 2a. So that would be negative 18 divided by 2, so that will be, really can just put that in my head as a negative 9, plus then the square root of the negative b over 2a quantity squared. So in this case, I don't need to worry about the minus sign since I'm squaring it, so I'll just put 9 squared minus the c over a. So in that case, that'll just be minus the 72. Now, I may want to check here that the argument is going to be positive, so that I will get a real number. And indeed, 81 minus 72, of course, is going to be a positive number. So that will, I don't have to worry then about whether I'm in the complex mode of my calculator, but I am actually in the complex mode. So even if this came out as a complex root now, that would still work. Okay, so I push enter. That's -6. We could have also done that probably in our head, but then I'll go back up to that expression and grab that again, and I'm going to go back and edit that slightly just by clicking here, change the plus to a minus for the other root because of course that's a plus and minus sign in front of the square root as in the quadratic formula. So now I'll change that to a minus sign, enter that. So my two roots are -6 and -12. Now we can of course check that by taking either one of those values and putting it into this original quadratic, such as here. So for example, -6 squared would be 36 minus 6 times 18. If you work that out, then that will in fact be 0. You might need a calculator to check that. And then -12 squared, 144 plus 18 times -12 plus 72. Again, you can verify that that will in fact be 0. So now we have to enter those numbers. And so remember, because we have a -6 and -12 are other roots, that means the factors are going to be s plus 6 and s plus 12. Okay, that's the way it works. And remember, that makes sense because if I multiply this out, I get s squared plus 6s plus 12s, which is going to make 18s, as I have here, plus the 6 times 12 is 72. If I had minus signs here, obviously that would not give us this expression. So it's very important to remember when the root is -6, that factor is going to be s minus that root, or s plus 6 and s plus 12. So that should be the answer there. So we'll check that. And that is correct. And now it's asking us to do a partial fraction expansion here. So again, it's not asking us for the time domain function as of yet. So important to be still working in the Laplace domain, because if you start putting in time domain terms, even if it's correct, it will not be accepted when it's asking for the Laplace domain. Okay, so to have a partial fraction expansion here, we're going to need two terms, two fractions, in other words, one with this as a denominator and one with this as a denominator. So I'll put in one fraction term here by clicking on that, or I could have drug it, plus a second fraction term. So that'll look like that. And then I need a constant in the numerator of each of those things. These will be real constants because my roots are real. And then I need the s plus a term in each of the denominators to make a proper partial fraction expansion. So now the a's we know are going to be 6 and 12, as we can read off from the original expression. And again, we're working with f of s here, not the full g of s. Okay, so now we need to find the coefficient in the numerator, which is the hard part here. And to do that, I'm going to use the method of residues, otherwise known as maybe the thumb method. So I'm going to multiply to find this coefficient, for example. I'll multiply the entire expression by s plus 6, and then set s equal to -6. And by doing that here, I'm going to get s plus 6, and then with s equal to -6, that makes it 0. So that gets rid of this entire thing and isolates, just leaving me this unknown here on the right side. So then when I multiply this times s plus 6, that's going to cancel this s plus 6. And of course, this is the reason we factor it, is to make that easy. And then I set s equal to -6. So I'll have -6 plus 12 here. So that would just be a 6 in the denominator. And then a -6 plus 11, so that'd be a 5. So I have 10 times 5 is 50 divided by 6, or 56ths. And it might be easy just to do that on a calculator, so I'll go 50 divided by 6, and that's 8.33. So I'll go ahead now and enter that as my coefficient, 8.33. And now for the other term, I have s plus 12, so I'm going to, in the denominator, so I'm going to multiply through by that and set s equal to -12, much as I did over here. And of course, when I do that, this term goes away, and I'm left with just the unknown coefficient here. The s plus 12 will cancel here, and then I set s equal to -12. So I'll have -12 plus 6, that's -6, And then a negative 12 plus 11 is negative 1. So negative 1 divided by negative 6 is just 1/6. And so I end up with 10/6, or reducing that, that would be 5/3. And then I probably know that that's just 1 2/3, or 1.67, say, to 3 decimal places. And then if you want to check that, of course, you can multiply through, put this over a common denominator. So you'd have 8.33 times s plus 12 plus 1.67 times s plus 6. And then you can verify that when you add those, that you would in fact get the original expression. Okay, so I'm going to check it here. That is correct. And now the final step here is to enter the expression in the time domain. So now I need to look at this and I say, well, I'm going to basically, because I have this g of s thing with this exponential factor, that in fact is time shifting. So that has the form e to the negative t naught s, where t naught is just 1 second in this case. And again, if you don't remember the time shifting property, that is available here. So that is this property right here that I'm using. So everything is time shifted. So that just introduces this basically shift of both of the unit step function and of the other function, the inverse transform of f of s. So I need to remember to do that. Okay, so because I have the time shifting, I'm going to need to use time shifted terms in the time domain. So I'll use this palette of terms, which are all time shifted the way that we need them. And so for the first term, I'm going to need a constant times a time shifted exponential, which is this. And then remember that I also need the time shifted unit step function. Now this function here, or that term rather, is one where you could insert everything inside the brackets, so you could maybe put both terms in there if you like. I'm just going to use separate functions here to make it a little bit simpler. And then I need to add to that the inverse transform of the second term, using the fact that the Laplace transform of the sum is the sum of the Laplace transforms of the individual term. That's the linearity property, which is available here if you don't remember it. And so now I need another constant times another time-shifted decaying exponential function times, again, the time-shifted unit step function here. Okay, so now let's go ahead and enter the values here. So the time shifting, as we see up here, then t naught is 1 because it's just e to the negative s. So that means it's shifted by 1 second here. The units are not shown explicitly, but that's what they are. And then also in there, in the exponential, I need the time shifting. And here I need the time shifting, and then in the other unit step function, since I used 2 different unit step functions there. Then the first coefficient would be the 8.33. And the second one would be the 1.67. And then the first term, I have s plus 6, which is my a, the 6. So it's e to the negative at. So it would be e to the negative 6. In this case, times t minus 1, because again, I'm using that time shifting property. And then the second one, it's s plus 12, so my a there is 12, so it would be e to the negative 12 times the t minus 1 argument. So that should be the complete answer, and that, in fact, is correct. Okay, and this gives me a brief summary of what I just did. If I want a more detailed solution showing all of the steps, in case I needed to review that, then I could click here. So right now I'm going to go ahead and work another problem. So we've done one of the 3 problems. Let's do the second problem type now. So this time, I'm going to give it another form here. And I might check as to what types of roots I'm going to have when I factor the quadratic terms. And I could check the discriminant, the b squared minus 4ac. So that would be 16 minus 4 times 20, or 80. So 16 minus 80 is obviously a negative number. So in this case, I'm going to actually have complex conjugate roots. So this is going to be a problem involving complex conjugate roots, which is a little bit more involved. So first, it asks me again to factor the quadratic terms in the numerator and denominator. It's only in the denominator here. So I need to stay in the Laplace domain because, again, it's asking me for another form of g of s, to just do this one step at a time, basically. So I'll need a fraction. and then I'll need a constant in the numerator, and an s plus a term multiplying that constant. And then the denominator, I'll need 2. And now, because I know those are going to be complex numbers, I'm not going to use s plus a, because a has to be a real number in this term. So if it's going to be a complex root, I need to use the s plus alpha plus j beta type of term. So I'll put that in there. And then I need a second term of that nature, which I need to make sure I get that down in the denominator. There we go. Okay, so now the numerator is going to be the same. So I just basically have -1 here. Or I could have used a minus sign, I guess, would also work. And s plus 7, so that's not going to change because I'm only factoring the denominator. Now, to do the factoring process, I'm just going to use a calculator here to make it easy. So let's do that and bring up a calculator emulator here. And let's clear that out. Okay, so it is important, since I'm going to have complex numbers, that I am in a complex number mode. Now notice here I can check that instead of saying real, it does say a plus bi. That means I'm in rectangular mode. I'd kind of like to have my numbers here in rectangular mode, because that's how I'm being asked to enter them there. So I'd want to make sure I'm in that rectangular mode. If you're not, you'd go into mode and just go down here to this row with the arrow keys here and go over and set that. And I would just hit enter to do that, but it's already done. So I'm just demonstrating what you would do if you were not already in that mode. If it says real, you're not going to get the right answers. It simply will not work properly. So you have to make sure that you're in that complex number mode, in rectangular mode here, because that's the format required in the answers. Okay, so let's exit that. And I'm going to use the standard quadratic formula, the formula I like to use. And notice that we have a equal to 1 here, b is equal to 4, c is equal to 20 in the coefficients. So the quadratic formula tells us negative b over 2a to begin with. That's the form that I like to use. So that means negative 4 over the a is 1, so it is negative 4 over 2. And I'll just do that in my head. That's negative 2. And then I have plus or minus, so I'll put a plus for now. And then I'm going to have a square root of that negative 2 squared. And of course, squaring it, I don't really need the negative sign, so I'm just going to put 2 squared. And then minus the c over a is the form that I use. So that would just be 20. And obviously we can see that 4 minus 20 is going to be negative 16. So I can kind of see the answer is going to be negative 2 plus or minus, well, in this case, plus 4i. But it'll tell us that. And then I know the other root has to be the complex conjugate of this. So I could just say it's negative 2 minus 4i. If you want to verify that, I suppose you can always go up and grab this expression and go back and edit it here, just to make that a minus sign instead. And of course, that'll give you the negative 2 minus 4i, as you'd expect. So those are our two roots. So now we have to remember, though, that this is what has to be subtracted from s to give you the factor. So in other words, I have to take the negative of these two values, putting in here. So I'm going to have s plus 2 minus 4i. So that means plus j. Since there's a plus sign pre-printed, I'll put j minus 4, which is allowed there. And then the other one will be, again, s plus 2. In this case, it'll be plus 4j. Okay, so again, very important to check the signs, because, and you can kind of verify that if you multiply that out, that for everything to work out and in fact give you this, if you multiply out all those terms, you have to have the signs that I've indicated there. So if you had s minus 2, for example, that would never give you the plus 4s. Okay, so that should be the result. So let's check that. That is correct. And now it's asking me to do the partial fraction expansion here. So notice, again, it's not asking you for g of t just yet. It's asking you for g of s. So I'm still going to be in the Laplace domain. And if I start prematurely entering the time domain answer, it'll be rejected because it's not what it's looking for. And it'll tell you that, but sometimes people don't read it and they just keep doing it again and again. So try to avoid getting frustrated by doing that. Okay, so for a partial fraction expansion, I'm now going to need two fractions, of course. So I'll put in one fraction plus a second fraction. And now I'm going to use a constant, but I need to use a complex constant because in general here the constants are going to be complex when I have complex conjugate roots. And in order to do the inverse transform easily, I want to use a polar mode version of that, because if I look at the formula for the inverse transform, that's really what's going to be needed. So I'll put that in there. And again, just to remind you of the formula we're going to be using, I'll go to the Laplace transform table. And basically, this is the formula we're going to be using. We're going to try to get in this form, we have a polar mode constants and this type of partial fraction expansion, which is basically what we're using now. And we're going to get this type of value. So we definitely want this to be in polar mode so we can easily determine the values of theta and the magnitude of k here. If we put it in rectangular form, we'd have to do additional work to get those values. Okay, so we have the constants, and then we need these linear terms with complex numbers. So again, don't try to use s plus a because a has to be entered as a real number. So it's the s plus alpha plus j beta, and of course we can make the beta positive or negative as need be. So now we need to do the math here, and notice that there are no real poles here. There's no additional factors, and so we don't need any third or fourth or whatever terms in the sum here. Okay, so we know that the factors are going to be the s plus 2 plus the, well, we could say minus j4, so we can put a negative 4 there. And then the second would be the s2 and the j4. So we just fill those in to match the original. And now the hard part, of course, is to determine these coefficients. Now you may remember that once we've determined one of these, the other was automatically going to be the complex conjugate of the first one. And that's just because that's how it always works out for these problems. And there's a proof of that in the introductory tutorial. But you can compute both if you like, but it's just not really necessary. Okay, so to get this, we're going to use the same method we used for real roots, which is we multiply by this denominator and multiply every term by that denominator. So that'll put the s plus 2 minus j4 in the numerator here. Then we're going to set s equal to negative 2 plus j4. And when we do that, of course, we're going to get 0 multiplying this. So this term goes away. And we're just isolating then this constant, complex constant that we need. So when we multiply through times the s plus 2 minus j4 here, that gets rid of this term. We can just put our finger over that if we want. And it'll leave us with the s plus 2 plus j4. And then we're going to set s equal to, again, the negative 2 plus j4 in both those terms. So in order to calculate that, I'm going to use my calculator here. This is the easy way to do that. So first of all, I have a negative 1 times, I'll just do parentheses here. And the s, remember, is going to be negative 2 plus j4. So I can do this in my head, really. So negative 2 plus j4, that's going to be give me 5 plus j4. So it's probably just easiest to do that. So 5 plus I4. So that's the numerator there. And then we're going to divide by the remaining term, which remember is this term, because we multiplied through by this. So that canceled this term. That term is gone now. So we're going to basically divide by the remainder. So we divide by and put a parentheses there. And remember, the s now is negative 2 plus j4. So the negative 2 and the plus 2 are going to cancel out. And then we have the plus j4. We're really going to have j8 is all that we have. So we can kind of do that in our head and just put in I8 in the calculator. Remember that in this calculator, the j is symbolized by I, the mathematician or physicist notation. Okay, so that should be the value. Now, I did make a mistake, however, because at this stage, I really want to have this in the polar form, and I'm still in rectangular mode. But that's okay. I don't have to erase this. I can just go into modes and change that before I click enter. That'll just save me converting it. So now I'm going to go down and change this into the polar mode, which would be much more convenient here. So I'll hit enter there and then clear. And now when I click enter here, it will give me the answer in the form I want it in, which is the polar mode form. Notice also that I'm in the degree mode here. It's very important to pay attention to your angular mode. I didn't mention that. But since I want to enter degrees here, I need to be in the degree mode here. Otherwise, I'd have to convert radians to degrees. And that's a common error, is to forget what mode you're in the calculator. So again, the modes are set here down in this line here, whether you're choosing radian or degree. Generally in Circuit Tutor, you're going to want to be in the degree mode to do those calculations. Okay, so there's my coefficient. So I'll enter that as 0.800, do at least 3 digits there. And then the angle would be 128.7. Just rounding that off a little bit. And then, as I say, we could compute this one, but really it's just going to be the complex conjugate of the first one. So I could just enter it that way and change the angle to the negative 128.7, because that's the complex conjugate, of course, of this number. You just change the angle, because that's, remember that this could also be written as 0.8 e to the j 128.7 degrees. So when you do the complex conjugate, you change j to minus j. Effectively, that just changes the angle to the negative of its original angle. So that should be the correct partial fraction expansion. So let's check that. And that is in fact correct. Okay, so now that we have that, we need to use the inverse transform formula. Now, I already had that pulled up here, but that's a little inconvenient to use, so I'm actually going to pull that up in a separate tab for convenience. So I'm going to open that link in a new window, and that way I can put it over here and look at it while I'm actually entering the equation. It might make things a little bit easier for you. So basically, starting from this, I need to, first of all, identify this as being the s plus alpha minus j beta. So you see which one has the minus sign. Well, it's this first term. If it was this term, then I would have to use this as my k. But in this case, it's this one, it's k, as opposed to, well, k angle theta, in other words, as opposed to this being k, because this has a plus sign here. And if you get those mixed up, you're going to basically get a minus sign or a negative value of the correct phase angle, and then that final answer would not be correct. Okay, so let's put in the form of the solution. So we're going to have some sort of constant. And again, that's going to be a real number because this is the magnitude of k. So I can just use a real number for that constant. And then next I'm going to need a decaying exponential term. And oops, I'm in the Laplace domain, aren't I? So I need to go into the time domain. Now the constant's the same in both cases, so that doesn't matter, but the other terms are different. So I have a decaying exponential, and then I need a cosine function with a phase shift, so that I'll use this term here. And finally, I need to make sure I use the unit step function, which is the u of t, and so I'll put that on last. If I forget that, it will be marked incorrect because it needs to have that unit step function to turn this on at the appropriate time. So now to evaluate the prefactor, I need twice the magnitude of k. So you see our magnitude of k is 0.8, so twice that would just be 1.6. I mean, you can use a calculator if necessary, but I don't need that here. Then the e value, it's e to the minus alpha t here. So I look for the thing that was added to the s, and that's the 2, the real number. So that's going to be e to the negative 2t. And then the beta is the thing that will appear in the cosine, what we oftentimes call omega, but here it's just being referred to as beta because of the way I denoted this. And again, that's going to come from the alpha minus j beta term. So the beta would be considered to be 4 here, not negative 4. So that's going to be 4. And then the phase angle, that's going to be this phase angle here. And again, this is where I have to be careful to pick the right one. So I need the s plus alpha minus j beta term to pick out the right phase angle. So it's going to be this one, not this one. So it's going to be plus 128.7 degrees. Okay, and before I check that, remember that it would almost never make sense to have a growing exponential here. This is indeed decaying because I have a negative exponent. So as t gets bigger, this gets smaller and smaller because it's 1 over e to the 2t, if you will. And as t goes to infinity, that's 1 over infinity, or 0. So that's what you would normally expect to get, unless you had, for example, the output of an unstable system or an unstable circuit. And that won't normally occur, at least not frequently. So that's what I should expect. And it would raise a red flag if I had e to the plus something here. Okay, so let's check that, and that is correct. So that will give me a brief summary of what I just did in that expression. And again, I can always view a detailed solution similar to what I would have in an example. So for right now, I'm just going to continue. And let's work now the third type of problem on this level. So in this case, it's a little bit more complex. Now I have actually a product of a quadratic term and a linear term. So I'm going to have certainly one real root, or one pole at -9 inverse seconds. I have a 0 at -12 inverse seconds. But now I need to figure out what these are. And let's see if those are going to be real or complex. So we can check the discriminant. B squared is going to be 64, since b is 8, minus 4ac. Well, that's 4 times 52 is going to be over 200. So clearly that's going to be negative. So I am going to have complex conjugate roots for this quadratic term. So again, the first step it's asking you to do, again, always read what it's asking before you enter the answer, is to factor the quadratic term. So basically, I need to have a fraction, and of course, I'm not going into the time domain. I'm staying in the Laplace domain just to factor that. So I need to have Laplace domain terms. So I go back here, and I'll need a fraction. And then I need a constant, which will be a real constant in this case. It's just 3 times the s plus a term. Oops, upstairs. And then I need, well, I do need another s plus a downstairs. And then multiplying that, I'm going to have, since these are going to be complex roots, I've already checked that, I'm going to need to use the s plus alpha plus j beta template for those, not s plus a, because again, a must be a real number always. So we'll put one of those down there. And then we need another one of those terms down there as well. And now I'll start to enter this. And so we have the 3 times s plus 12 is just the numerator. And now I need to, well, I have a s plus 9. That's just staying the way it is. And this is where I'm factoring. So once again, I might want to use a calculator to factor that. So let's do that. And use my calculator here. So again, I'm going to use the quadratic formula, which is a is 1, b is 8, and c is 52. So the negative b over 2a is going to be negative 8 over 2. And so that's going to be a negative 4 plus the square root of that same thing, that negative 4 squared, which is the same, of course, as 4 squared. So I won't worry about the negative sign there. Minus the c over a, which in this case is just 52. And obviously 16 minus 52 is going to be negative. As I predicted, these are going to be complex roots. So again, I want to be here in the rectangular mode, however. Notice I'm still in the polar mode, so I will need to go back and change my mode. If I'm in the real mode, definitely nothing will work here because it's not designed to take square roots of negative numbers in the real mode. So you must be in the complex mode. So we'll go down here and put that into rectangular mode since that's the form that I need for my answer. And now I can verify that I'm in rectangular mode. So now I'll press enter, and I have negative 4 plus 6i. So that's going to be one of the roots. And the other one I know already is going to be negative 4 minus 6i because it has to be the complex conjugate of this one. And that's just from the fundamental theorem of algebra, the fact that all these coefficients are real, so therefore any roots of that quadratic must be complex conjugate pairs. Okay, you cannot have general complex numbers unless these coefficients were themselves complex, which is not the case. Now, if I'm not sure about that, I could always go back up and just grab that expression and then go over and edit, change that plus sign to a minus sign to get the other root. And that would verify. But in any case, I know that's true. So now, for this root, for example, negative 4 plus 6i, remember that that factor then will be s plus 4 minus 6i, because that's what you do when you have roots in order to get the factors. You have to subtract this value, not add it, because that wouldn't work if you added it. So I'm going to have s plus 4, and then I have minus 6i, so I'm going to put a negative 6 there. And then over here I'll have the same thing, s plus 4, but this time it'll be plus j 6. So those are complex conjugate terms. So we'll check that factored form now. That is correct. And the next step will be do the partial fraction expansion. So again, I'm going to be entering something in the S domain, so I would not use these time domain terms at this point. Okay, I'd only use Laplace domain terms. So for a partial fraction expansion, I see that I have 3 poles now, 2 complex ones that are a complex conjugate pair, and then a third one. So I need to have 3 terms. So I'll add one fraction plus another one plus a third one. Okay, and then for the first one, the s plus 9 term, I need a real constant, and then I'll have an s plus a there. And then for the second term, now I'm going to need a complex constant, and I want it to be in the polar form for ease in using the formula as I showed in the last example. So I'm going to put a polar form there and another polar form constant here. These are complex constants. Remember, you can't use k for a complex number. That's intended to be a real number. And again, the little tooltip that there you notice pops up sort of reinforces that's a real constant. This one's a complex constant in rectangular form. This is a complex constant in polar form. Okay, so now also we need a term that has a complex root, so we need like an s plus alpha minus, well, plus j beta, another term like that. So now we've set up the general form that we need, and now we need to compute those coefficients. So first of all, we'll enter the values here, which would be s plus 9, and then this will be s plus 4 minus j6, so it'll be a negative 6 here, and this one will be s plus 4 plus j6. So that would correspond to each of those 3 factors in the denominator. And again, the goal is to get this so that if we put all of this over a common denominator, that we would recover the original thing. And that's actually a way to check when you've done this. For example, if you're taking a test and you have to do this, then you could check that to make sure you didn't make a mistake doing the partial fraction expansion. So let's start out and use, once again, the method of residues, or the thumb method if you like. So to find this first constant of the real term, I'm going to multiply through by s plus 9 and then set s equal to negative 9. So that'll multiply both of these terms by the s plus 9, and then when s is negative 9, that multiplies them by 0, so they go away, and I'm left with this one constant that I want. So when I multiply this expression by s plus 9, that of course cancels out the s plus 9, and I can just put my thumb over that if I want. And then I set s equal to negative 9. So now I have to do some calculations here, so I'm going to do that on the calculator. So that'll be a 3 times the first factor. Well, really, I can just do that in my head. So the negative 9 plus 12 would be 3. So I can just say 3 times 3 divided by, and this term, remember, is gone. It's canceled. So I'd first have this term, and when I set s equal to negative 9, that will be negative 9 plus 4 is negative 5 minus j6. So I'm going to push negative 5 minus I6. And then remember that since I didn't put parentheses here, I'm going to divide again to make sure that's in the denominator. That's just standard notation. And otherwise, I could have, if I want to make these into a product, I would have had to have parentheses around the entire thing. So be very careful with parentheses always. Okay, so then I'll have the other factor, which is going to be the negative 9 plus 4. So again, that's negative 5 plus j, well, I6 in this case. So negative 5 plus the I6. Okay, and then think about what form I want that in. Well, it's going to be a real number, so it actually won't matter. I'm multiplying a number times its own complex conjugate, so that will give me a real number. So the form here doesn't really matter. So that's going to give me a value of 0.1475. So I'll enter that here. And now I need to compute the second constant here, this one. So to do that, I'm going to multiply through by the denominator again, the s plus 4 minus j6, and then I'll set s equal to negative 4 plus j6. And that will, of course, multiply both of these things by 0, so they go away. And then when I multiply by this s plus 4 minus j6, that will cancel out this middle term here. So you can imagine putting your finger over that. And that'll be this numerator and this term and this term. So once again, I'm going to evaluate on the calculator. So I first have the 3. And parentheses, now I'm going to have, since I'm multiplying by the s plus 4 minus j6, I'm going to set s equal to negative 4 plus j6. So I'm going to have, and I'll just, for simplicity, I'll just write that out explicitly. So negative 4 plus I6, and then I have plus 12. I mean, obviously I could have combined the two real numbers in my head, but I just put them here. And then that's going to be divided by this first term in the denominator, the s plus 9 term. So I'll put parentheses there. And again, the s is going to be the negative 4 plus j6. So negative 4 plus 9 is 5 plus j6. So I have 5 plus I6, close parentheses. And again, I want this in the denominator, the last term, so I'll divide again and have parentheses. And now I have this term. So when I set the s equal to negative 4 plus j6, the negative 4 cancels with the plus 4, and then the j6, I'm going to end up with j12, basically. So I have I12 there. And that should be the complete expression. So now remember that I want this one now in polar form. So I do need to change my mode before I evaluate that. Otherwise I have to reevaluate it. So I'll just change right away to polar mode. Just make it a little easier. And now I'll press enter. And that gives me the value in polar mode. So this constant will be 0.32. And then the phase angle is negative. And notice, again, I am in degree mode. It's very important to know what angle mode you're in here because that'll affect the output here. So this is negative 103.3 degrees. And that's that value. Now, I could do a similar computation for this if you like, but it's really not necessary because we know that this will always be the complex conjugate of this. And so instead of repeating the calculation, I'll simply write in the correct value, which is 0.32, times the negative of this angle, which is now going to be 103.3. Okay, so that should be the correct partial fraction expansion. So I'll just click check equation there. And that is correct. Okay, so now the final step here is to find the g of t. So now we're going to go into the time domain. So we need to use time domain terms now. So I'll go over to this palette. And remember that there was no exponential factor, so we're not going to use time-shifted terms here. So now for the g of t, we need to find the inverse transform each of these three terms. So the first term, that's a very familiar one, hopefully by now. That should just be a 1 over s plus a type term. So that's going to give us an exponential times the unit step function. And I could use this term here and put everything inside those brackets, but I'm just going to do individual to make it simpler. So I'll need a constant times the decaying exponential times the unit step function for the first term here. My constant will be the 0.1475. And then the a value will be 9 because it's s plus a, so it's e to the minus at, so e to the negative 9t. And remember that exponentials should normally decay with time, not grow. So if you had an e to the plus something t, that would be a very big cause for concern there and probably indicate that something's wrong. Okay, so now that's the first term, and then I'm going to add to this. And now I can again go look at that table here and bring up the formula that I'm going to use for the inverse transform of the second two terms together. So those two terms together will give us one time shifted, or phase shifted rather, cosine term. And again, I don't want to use a separate cosine and sine term like you might have learned to do in differential equation class, because that really obscures the phase relationships. And electrical engineers always want to know the phase relationships between different signals. And this phase shifted cosine term, therefore, is the preferred term. So we don't want to be using, for example, things like this, as you may have learned to do in math class. Okay, so we're going to use this term, and so now we're going to first of all need a constant, and this is going to be a real constant because that's a magnitude. So again, we'll just pick a k there. And then we need the decaying exponential, so that will be this term. And then we need a phase-shifted cosine term, so that will be this term. And finally, we need the unit step function. And you don't want to ever forget that because that's important. Okay, so our constant is going to be twice the value of the k, which was 0.32. So we can easily use that as 0.64. So again, it's twice this because it's 2 times that magnitude, and that is the magnitude of that constant. And then the a is going to be the value here. So it's alpha really. So it's s plus alpha minus j beta. So the alpha there is a plus 4, and that will give us a decaying exponential. Again, any growing exponential will be highly suspect in answer to this. So you'd always want to make sure you have decaying exponentials. So your cosine function there, that's the minus j beta, and so the beta would be 6 here, which we often call omega, but in this case it's being called beta. And now the phase angle, that's the tricky one. We've got to make sure that we use the correct term because there's 2 different phase angles here that are negatives of each other. So we want the term for the phase angle that is over the s plus alpha minus j beta, where alpha and beta are always assumed to be greater than 1. So that would be this term, and so it's negative 103.3, not the plus 103.3. Okay, so that should be the complete expression in the time domain for this problem. So we'll check that. And that is correct. So now it gives us a brief summary. Again, if you wanted a more detailed solution showing you all of the steps, you can always click there and get those details. But basically that concludes the hard level on this exercise.